Okay, so first let's start with some simple logistic regression. Now, recall when we said simple linear regression, we talked about predicting our response variable based off of a single predictor variable. Same thing in logistic regression. So we're going to make some predictions based off of a single predictor variable, and this will just allow us to understand what's going on with the coefficients and kind of how to interpret that. So we're going to train two models here. You can see that we train one on the left here. We use the logistic regression model function, right? That's going to create our model object. And we're just using the default engine, which is GLM, to do so. And now we're going to fit on our attrition data. It's the attrition variable is a function of monthly income. And on the left-hand or right-hand side, we create another model where attrition is a function of overtime. Okay, whether or not the employee works overtime. Now, once we fit these models, you can see that we can actually make predictions in two different ways. Okay, so we again use the predict algorithm here, and we can say type equals prob. This means we want to predict the actual probabilities of our response variable. So recall our response is attrition, whether or not the employee is going to leave. So now when we use this prediction type, we'll get a data frame that's got two columns. One, the probability for not attriting or leaving, and the other one is the probability of leaving. Okay, so you can see that we'll have for the first employee, the probability of leaving is 0.216 or 22%. The probability of staying and not leaving is 78. Right, and we go right on down. Now here's the thing. We can also use this to predict class, right? So type equals class. And that just means what are we going to classify this between our binary responses? So what it uses is the cutoff of 0.5. So when the probability of an observation or predicted value is greater than 0.5, that it is going to occur. So in this case, if the probability of the employee leaving equals yes, is greater than 0.5, then we will predict yes, otherwise we predict no. So when we use this class, you can now see we get our binary response variables. In this case, the first 10 observations that we're predicting on, all were predicted to not leave, right? And if we looked over here, we can see that the prediction for no is all greater than 0.5, so that's why we're predicting no. If an observation had this prediction equals yes greater than 0.5, then we would in fact be returning the value yes for the class. All right, so now let's kind of look at the model output. So recall that we could get the coefficients with linear regression. We can do the exact same thing with logistic regression. Now, what happens here is we get our model output, and we can see we have our coefficient estimates, right? In this case, it's negative 0.000139 for the monthly income model, and for the overtime model, it is 1.9. Now, these are very difficult to interpret because actually these coefficients are in log odds scale. We actually call that logit scale, and it's very difficult to understand. However, if we make a transformation of these coefficients, particularly, or specifically, let's take the exponential transformation of our coefficients. Now we see a new value for monthly income, 0.999. And on the right here, we take the exponentiate the coefficients for our second model, and we see overtime yes equals 3.63. So these values right here are easier to interpret. We call these, or we say that these are the multiplicative impact to the odds of the response variable. And I know that that's a whole lot of stuff there packed in that short sentence. But what that means is as our monthly income increases, then the impact to the odds of the response variable is 0.99. Whereas in this case, when our employee ends up working overtime, there's a 3.63 increase in the odds of the employee leaving. So all this means is if you have a value that is less than 1 when we do this transformation, we are actually seeing a decrease in the odds of the response variable. If it's greater than 1, we're seeing an increase to the odds of the response variable. If we visualize this, it'll be a little bit easier to interpret. So here we have two plots. The one on the left here is as monthly income increases, we see the effect it has on the probability of attrition, which is what we're trying to model. And we can see that it continues to decrease. And that's because when we go from a monthly income of, let's say, $5,000 to a monthly income of $5,001, we actually see a decrease in the probability. If we were to take the probability of attrition at 5,000, we would now take that probability times 0.999, and that would become the new probability of attrition when we have a monthly income of $5,001, right? So since we're multiplying this by less than 1, we see this steady decrease in the probability of attrition. Now on the right-hand side, it was the model where whether or not the employee works overtime and that impact on attrition. And we can see that here the probability of attrition when they don't work overtime is, let's say, roughly 0.1, 0.12, right around there. But however, if the employee does start to work overtime, we see that there is a 3.6 times increase in the probability of attrition, or the odds of attriting. Right? So we can see that since this is a large number, that means the odds are actually increasing over 3-fold times when we add in this new parameter.